Many of us are very familiar with our home galaxy, the Milky Way. Home to the Earth, our solar system, and our closest neighbors in space, the Milky Way is vast. But in order to truly understand our place in the universe, we need to take a step outside our galaxy. What lies beyond the bounds of the Milky Way? How much more is there to the universe outside of our most familiar surroundings? A large collection of galaxies known as the local group are a part of the answer to this question, and they form our cosmic neighborhood. The local group is a gravitationally bound family of more than 80 galaxies, ranging from massive spirals like the Milky Way and Andromeda to tiny faint dwarf galaxies barely visible even with powerful telescopes. By studying these galaxies and their interactions, astronomers can uncover the history of our own galaxy, the forces that shape galaxies, and the larger structure of the universe itself. Over the course of this episode, we'll journey through this remarkable collection of galaxies, exploring their size, their shape, and the stories they tell about the cosmos beyond our familiar skies. Let's start with a definition. What is the local group? The local group is a collection of about 50 to 80 galaxies, with new discoveries still being made, with a diameter of roughly 10 million light-years. While the Milky Way is our home galaxy, it shares this neighborhood with other massive members like the Andromeda Galaxy, which is slightly larger than our own, and the Triangulum Galaxy, a smaller spiral that orbits near Andromeda. Surrounding these giants are dozens of dwarf galaxies, small, faint systems that often go unnoticed, but play a crucial role in understanding how galaxies form, interact, and evolve over time. So if the local group is made up of several independent galaxies, what prevents them from drifting apart? The answer lies in the local group structure. The galaxies of the local group are not scattered randomly through space. They are gravitationally bound, held together by the combined pull of their mass. This means that, despite the universe's expansion, the galaxies in this neighborhood move slowly around a common center of mass, orbiting one another over billions of years. The Milky Way, Andromeda, and their satellites each have their own smaller systems of dwarf galaxies, but all of these members are connected in a delicate cosmic dance. Some dwarfs orbit closely, while others drift along more distant paths, yet all remain part of this cohesive family. Being gravitationally bound gives the local group its structure and stability, keeping its members from simply drifting apart into the vastness of space. At this point, you may be thinking, what is the point of studying the local group? These galaxies are so far away, tens of millions of light-years in fact. How could they represent anything important to science? The answer is that the local group is close enough for us to study in remarkable detail, yet diverse enough to reveal the fundamental processes that shape galaxies. By observing how galaxies interact, orbit, and even collide, scientists can learn how galaxies grow, merge, and evolve over billions of years. The motions of galaxies in the local group also provide critical evidence for dark matter, the invisible substance that makes up most of the universe's mass. For example, some dwarf galaxies move in ways that cannot be explained by visible matter alone, revealing hidden gravitational forces at work. Studying these galaxies also helps us calibrate our measurements of distance and motion across the cosmos, giving astronomers the tools to understand the structure and expansion of the universe. In essence, the local group is our cosmic laboratory. It allows us to explore the past, observe the present, and even predict the future, including the eventual collision between the Milky Way and Andromeda, billions of years from now. By studying this neighborhood of galaxies, we gain insight not only into our own galaxy's history, but also into the forces and processes that govern the universe as a whole. Before we had powerful telescopes and modern astronomy, distant galaxies were invisible as separate islands in the cosmos. Astronomers peering through early telescopes saw faint, hazy objects in the night sky, and they called them spiral nebulae, unsure whether they were part of our Milky Way or entirely separate systems. Were these strange clouds simply clusters of stars and gas within the Milky Way, or were they something far more distant and immense? For centuries, this question fueled heated debate. Some scientists argued that the Milky Way contained the entire universe, that everything we could ever observe was confined to our home galaxy. Others suspected that these nebulae might be island universes in their own right, vast systems of stars lying far beyond our own. The telescopes of the 18th and 19th centuries weren't powerful enough to settle the matter, and so the spiral nebulae remained enigmatic, suspended between two competing worldviews. This uncertainty would eventually be broken in the early 20th century, when astronomers like Edwin Hubble revealed that these faint spirals were not small clouds nearby, but galaxies millions of light years away, reshaping our understanding of the cosmos forever. Hubble used the most powerful telescope of his time, the 100-inch Hooker telescope at Mount Wilson Observatory in California. When he carefully examined photographs of Andromeda, he made a groundbreaking discovery. Among the faint smudges of light, he identified a special kind of star known as a Cepheid variable. Cepheids pulse in brightness in a predictable pattern, and crucially, the length of their cycle can be used to determine their true luminosity. By comparing how bright they appear from Earth with how bright they actually are, astronomers can calculate their distance. When Hubble measured the Cepheids in Andromeda, the results were staggering. They weren't just a few thousand light-years away, as would be expected if Andromeda were a small cloud inside the Milky Way. Instead, they were over 2 million light-years distant, far outside the bounds of our galaxy. This single calculation proved that Andromeda was not a nebula within the Milky Way, but a galaxy of its own, containing billions of stars. This discovery shattered the long-held belief that the Milky Way encompassed the entire universe. For the first time, humanity understood that our galaxy is just one of many, and that the universe is vastly larger than previously imagined. Hubble's work did more than solve a centuries-old debate. It opened up an entirely new field of astronomy, where galaxies became the fundamental building blocks of the cosmos. The Andromeda breakthrough also laid the groundwork for identifying the local group, the collection of galaxies that includes both the Milky Way and Andromeda. What was once thought to be a solitary galaxy surrounded by mysterious nebulae was revealed to be part of a much larger family, setting the stage for modern cosmology and our understanding of the expanding universe. Once Edwin Hubble had demonstrated that Andromeda and other spiral nebulae were in fact entire galaxies, astronomers began to see the universe in a new light. No longer was the Milky Way the entirety of the cosmos. Instead, it was just one galaxy among countless others scattered across space. But this new understanding also raised an important question. If the Milky Way is not alone, how exactly does it relate to the galaxies around it? By the mid-1930s, astronomers began to recognize patterns in the distribution of galaxies. Edwin Hubble and Walter Baade, both working at Mount Wilson Observatory, noticed that the Milky Way and Andromeda were not isolated, but part of a small collection of neighboring galaxies, including the Triangulum Galaxy and several dwarf companions. In 1936, in Hubble's book, The Realm of the Nebulae, The term local group appeared for the first time to describe this collection. It was a simple but powerful idea that galaxies, much like stars, are not evenly spread out through space, but often gather into groups, clusters, and even superclusters bound together by gravity. Hubble and Barde identified about a dozen galaxies as members of the local group, though today we know the number is far higher, between 50 and 80, with new dwarfs still being discovered on the edges of the system. Their identification of the local group was a turning point because it established the idea that galaxy groupings could be studied as units, not just as individual objects. This shift in thinking allowed astronomers to examine the dynamics of galaxies as systems interacting with one another, orbiting, merging, and evolving together over cosmic time. By coining the term local group, Hubble and Baade gave structure to our cosmic neighborhood. Just as a map of Earth begins with continents and then expands outward to the entire globe, the local group became the first map of our galaxy's place in the wider universe. It was an essential step in moving from the discovery that other galaxies exist to understanding how they are organized, a foundation that still shapes modern cosmology. Today, measuring the distances to galaxies combines classical techniques like Cepheid variables and redshift, with cutting-edge technology and observations across the electromagnetic spectrum. While Cepheids are still used for nearby galaxies, modern telescopes, both on Earth and in space, allow astronomers to detect even fainter stars and distant cosmic standard candles, such as Type 1a supernovae. These exploding stars have a well-known intrinsic brightness, so by comparing how bright they appear from Earth, scientists can calculate their distances with remarkable precision, often spanning billions of light-years. For galaxies too distant for individual stars to be resolved, redshift measurements remain a cornerstone. By observing the light from a galaxy and analyzing how its wavelengths stretch due to the expansion of the universe, astronomers can determine its recessional velocity. Using updated values for the Hubble constant, this velocity is converted into a distance estimate. Modern surveys, like the Sloan Digital Sky Survey and the James Webb Space Telescope, combine redshift data with advanced computer modeling to refine these measurements and map galaxies in 3 dimensions. In addition, astronomers now use gravitational lensing, where the gravity of a massive galaxy or cluster bends light from a more distant galaxy to estimate distances and even measure dark matter. Techniques like these allow astronomers to create detailed maps of galaxy groups, clusters, and superclusters, providing a clear picture of the cosmic web and helping us understand the structure and evolution of the universe like never before. Now that we've covered a bit of the history behind the local group, let's go over what exactly makes a galaxy group. The universe is organized in a vast, layered hierarchy, with structures nested within ever larger structures. At the smallest scale are stars, the luminous spheres of gas that make up galaxies. Stars often form in clusters, but the true building blocks of the cosmos are the galaxies themselves, massive systems containing billions or even trillions of stars, along with gas, dust, and dark matter. Galaxies are rarely isolated. Many exist in groups, collections of a few to a few dozen galaxies bound together by gravity. The local group, which includes the Milky Way, Andromeda, and dozens of smaller dwarf galaxies, is one such example. Groups can merge or interact, their members orbiting a common center of mass and sometimes colliding in dramatic cosmic events. Larger still are clusters, which may contain hundreds or thousands of galaxies, all gravitationally linked. Clusters themselves are often part of superclusters, enormous regions of space where clusters and groups form sprawling filaments and walls. These superclusters trace the large-scale structure of the universe, forming a cosmic web of galaxies separated by vast voids. Understanding this hierarchy is crucial for modern astronomy. By studying each level, from individual stars to superclusters, we can see how the universe organizes itself and how structures evolve over billions of years. The local group is a diverse collection of galaxies, but its structure is dominated by three massive spiral galaxies: the Milky Way, Andromeda, and Triangulum. The Milky Way, our home, contains roughly 100 to 400 billion stars, along with gas, dust, and a supermassive black hole at its center. Andromeda, slightly larger than the Milky Way, is on a slow collision course with us, destined to merge in about 4.5 billion years. Triangulum, the smallest of the three spirals, orbits near Andromeda and may be gravitationally bound to it, forming a sort of mini-subgroup within the local group. These three giants contain the bulk of the mass in the local group and exert significant gravitational influence over the smaller galaxies nearby. Surrounding these spirals are dozens of dwarf galaxies, tiny and faint compared to their massive neighbors. Some, like the Large and Small Magellanic Clouds, orbit the Milky Way, while others, such as M32 and NGC 205, orbit Andromeda. Many dwarf galaxies are irregular in shape or spheroidal, containing far fewer stars than the spirals. Despite their size, these dwarfs are scientifically valuable. They are often relics of the early universe, providing clues about galaxy formation, star formation history, and the distribution of dark matter. The local group is not just a random assortment of galaxies, it has structure and organization. The Milky Way and its satellites form one subgroup, Andromeda and Triangulum another, with dwarf galaxies scattered throughout. All members are gravitationally bound, moving in a slow cosmic dance that has continued for billions of years. Together, the spirals and dwarfs form a neighborhood that is both diverse and interconnected, a laboratory for understanding galaxy interactions and the evolution of cosmic structures. The universe has been expanding since the Big Bang, with galaxies generally moving away from each other as space itself stretches. This expansion raises an interesting question. If the cosmos is constantly growing, why don't galaxies in the local group drift apart? The answer lies in gravity. Gravity is a powerful force that acts between all masses, and within the local group, it is strong enough to overcome the effect of cosmic expansion. The Milky Way, Andromeda, Triangulum, and their surrounding dwarf galaxies are all gravitationally bound. Their mutual attraction keeps them orbiting one another in a slow, intricate dance, rather than being pulled apart by the stretching of space. This balance explains why, even though the universe is expanding on large scales, local systems like the local group remain coherent. On the scale of galaxy groups and clusters, gravity dominates. Only at distances of hundreds of millions of light-years or more does cosmic expansion start to outweigh gravitational attraction. In essence, the local group is a cosmic island in an expanding universe, a neighborhood of galaxies held tightly together by gravity, while the space beyond continues to stretch outward. While the local group is our cosmic neighborhood, it is just one of many galaxy groups in the universe. For example, the M81 group, located about 12 million light-years away in the constellation Ursa Major, contains several large galaxies, including the spiral M81 and its companion M82, along with numerous dwarf galaxies. Similar to the local group, The M81 group is gravitationally bound, with its members orbiting one another and interacting over billions of years. Another nearby example is the Centaurus group, roughly 13 million light-years distant, which contains the massive elliptical galaxy Centaurus A and several smaller companions. Like the local group, this group exhibits a mix of galaxy types, spirals, ellipticals, and dwarfs, all held together by gravity. Comparing these groups helps astronomers understand both the diversity and common patterns in galaxy organization. While the local group is dominated by its 3 large spirals and numerous dwarfs, other groups may have different arrangements, with ellipticals or more active star-forming galaxies taking a central role. Studying these nearby groups allows scientists to see how local conditions, galaxy interactions, and dark matter distributions influence the structure and evolution of galaxy groups, placing the local group in a broader cosmic context. Having explored the local group as a whole, from its massive spirals to its dozens of dwarf galaxies, let's now take a closer look at its 3 largest members, the Milky Way, Andromeda, and Triangulum, and see what makes each of them unique. The Milky Way is our home galaxy, a vast spiral containing roughly 100 to 400 billion stars, along with enormous clouds of gas, dust, and dark matter. Its structure includes a central bulge, spiral arms, and an extended halo that stretches far beyond the visible disk. At the very center lies a supermassive black hole, Sagittarius A star, weighing millions of times the mass of the Sun. Our solar system resides in one of the spiral arms, about 27,000 light-years from the galactic center. The Milky Way's stars, gas, and dark matter are all bound together by gravity, forming a coherent system that has been evolving for over 13 billion years. Beyond its visible structure, the Milky Way is orbited by dozens of smaller dwarf galaxies, including the large and small Magellanic Clouds. These satellites provide clues to how galaxies form and evolve, and they play a role in feeding material into the Milky Way over cosmic time. Studying our own galaxy gives astronomers a detailed template for understanding the dynamics, star formation, and chemical evolution of spiral galaxies throughout the universe. The Andromeda Galaxy, also known as M31, is the largest galaxy in the local group, slightly larger than the Milky Way. Like our galaxy, it is a spiral with hundreds of billions of stars spread across its bright, well-defined arms. Andromeda is located roughly 2.5 million light-years away, making it the nearest large galaxy to the Milky Way. It is slowly moving toward us at about 110 kilometers per second, and in approximately 4.5 billion years, it will collide and merge with the Milky Way in a spectacular galactic event, forming a massive elliptical galaxy over time. Andromeda also hosts numerous satellite galaxies, including M32 and M110, and its outer halo contains streams of stars left over from past mergers. Observing Andromeda helps astronomers understand the structure and evolution of spiral galaxies similar to the Milky Way. Its size, shape, and future collision with our galaxy make it one of the most important objects in the local group, providing a glimpse into the long-term dynamics and fate of galaxies in gravitationally bound systems. The Triangulum Galaxy, or M33, is the smallest of the local group's 3 major spirals. It is located roughly 3 million light-years away, near Andromeda, and may be gravitationally bound as a satellite of its larger neighbor. Triangulum is less massive than the Milky Way or Andromeda, containing tens of billions of stars, but it is still an active site of star formation, with bright nebulae and dense star clusters scattered throughout its spiral arms. Its relatively small size and lower mass mean it has a weaker gravitational pull, making it more susceptible to interactions with neighboring galaxies. Despite this, Triangulum plays an important role in the local group, as its interactions with Andromeda and its dwarf companions provide astronomers with a laboratory for studying galaxy dynamics, star formation, and the effects of tidal forces over cosmic time. Observing Triangulum offers insight into how smaller spiral galaxies survive and evolve in the gravitational influence of larger neighbors. Each of these 3 galaxies deserves an entire deep dive, which we'll cover in future videos. While the Milky Way, Andromeda, and Triangulum dominate the local group in size and mass, the majority of its members are actually dwarf galaxies. These small, faint galaxies are easily overlooked, often containing only a few million or a few billion stars, compared to the hundreds of billions in the giant spirals. Dwarfs come in various shapes, from irregular blobs to smooth spheroidal forms, and many orbit the larger galaxies as satellites. Despite their diminutive size, they are an essential part of the local group's structure, providing a dense network of smaller companions that reveal the gravitational relationships within the group. Many of these dwarfs are difficult to detect because they emit very little light, and their stars are spread thinly across space. Only with sensitive modern telescopes and wide-field surveys have astronomers been able to uncover their presence. Observing these faint galaxies helps astronomers fill in the picture of the local group, understanding not just the giants, but the smaller, subtler components that make up our cosmic neighborhood. The local group hosts dozens of dwarf galaxies, many of which orbit the Milky Way or Andromeda. Around the Milky Way, familiar examples include the large and small Magellanic Clouds, visible to the naked eye from the southern hemisphere. These irregular dwarfs are active sites of star formation, glowing with bright nebulae and clusters. Other Milky Way satellites include the Sculptor, Fornax, Leo Phoen and Attu, and Draco galaxies, most of which are spheroidal and much fainter. Andromeda also has its own collection of dwarfs, such as M32 and NGC 205, along with smaller spheres scattered around its halo. Many of these galaxies are tiny and diffuse, discovered only in recent decades thanks to deep sky surveys like the Sloan Digital Sky Survey and Pan-STARRS. The discovery of these faint companions has nearly doubled the known members of the local group in the past 20 years, highlighting how much remains to be explored even in our cosmic backyard. Though small, dwarf galaxies play an outsized role in the evolution of larger galaxies. Over billions of years, mergers and interactions with dwarfs provide fuel for star formation, contributing gas, dust, and even stars to their larger hosts. Streams of stars stripped from dwarfs can trace the gravitational history of a galaxy, offering clues about past interactions and collisions. In addition, dwarfs act as a laboratory for studying dark matter, as their motions are dominated by invisible mass. By observing these tiny galaxies, astronomers can reconstruct the hierarchical growth of galaxies, seeing how massive spirals, like the Milky Way and Andromeda, built up their mass over time through repeated interactions with dwarfs. The study of dwarfs thus connects the smallest scales of star systems to the largest scale dynamics of galaxy groups, bridging the gap between individual stars and the structure of the local group itself. With an understanding of the local group's layout, gravitational center, and the precise motions of its members, we can now explore its largest galaxies and their smaller companions in greater detail. seeing how each contributes to the structure and evolution of our cosmic neighborhood. The local group is not just a random collection of galaxies, it has a clear three-dimensional structure. Observations show that the group is organized into two main subgroups, one centered around the Milky Way and its satellites, and the other around Andromeda and its companions. The Milky Way system includes our home galaxy, the large and small Magellanic Clouds, and other dwarf galaxies like Sculptor, Draco, and Fornax. The Andromeda system is similarly structured, with Andromeda at its core, the Triangulum galaxy nearby, and numerous smaller satellites orbiting around both. The Triangulum galaxy occupies a somewhat peripheral position. While it is close enough to Andromeda to be gravitationally influenced by it, it lies on the outskirts of the subgroup rather than at the center. Its position suggests it may have been a more independent galaxy in the past, now slowly being drawn into Andromeda's gravitational sphere. Overall, the local group spans roughly 10 million light-years across, but most of the mass is concentrated in the two dominant spirals. The dwarf galaxies form a scattered population between and around these subgroups, creating a complex, loosely connected network. Understanding this three-dimensional layout is crucial for studying the motions and interactions of galaxies. While the Milky Way and Andromeda dominate the gravitational landscape, the peripheral dwarfs provide insight into the history and evolution of the group over billions of years. To fully grasp the dynamics of the local group, it helps to consider its gravitational center, which lies somewhere between the Milky Way and Andromeda. The local group, though sprawling, is gravitationally bound, and its motion is dominated by the two largest members, the Milky Way and Andromeda. Astronomers estimate that the gravitational center, or barycenter, of the group lies somewhere between these two spirals, roughly along the line connecting them. This center is not a physical object, but a point that represents the balance of mass in the system. All galaxies in the local group, including Triangulum and the many dwarfs, orbit this common center of mass in complex trajectories shaped by the combined gravitational pull of the giants. Over billions of years, this gravitational dance will lead to increasingly close interactions, culminating in the predicted Milky Way-Andromeda collision, which will eventually form a massive elliptical galaxy. Even the smaller dwarf galaxies are affected, their orbits perturbed and sometimes disrupted by tidal forces, leaving behind streams of stars that trace the history of these interactions. Understanding the gravitational center is essential for modeling galaxy motions and predicting future events. By knowing where the center lies, astronomers can calculate the orbits of satellites, estimate merger timescales, and reconstruct past interactions, giving a more complete picture of the local group's evolution. Modern technology has greatly improved our ability to track these motions, particularly through proper motion measurements from satellites like GAIA. One of the challenges in studying galaxy dynamics is that most measurements of distant galaxies only provide radial velocity or motion along the line of sight. To fully understand how galaxies move in 3 dimensions, astronomers need proper motion data, which measures motion across the sky. The European Space Agency's GAIA satellite has revolutionized this field. Launched in 2013, Gaia is capable of extremely precise measurements of stellar positions and motions, including stars in nearby dwarf galaxies and the outer regions of the Milky Way and Andromeda. This data allows scientists to track not only the movement of individual stars, but also the motion of entire satellite galaxies relative to their hosts. By combining proper motion measurements with radial velocities, astronomers can refine models of galaxy orbits, the gravitational influence of dark matter, and the location of the local group's barycenter. For example, Gaia's data have helped confirm that the Milky Way and Andromeda are on a collision course, and that the orbits of dwarf galaxies are more complex than previously thought. These measurements are transforming our understanding of the local group from a static snapshot into a dynamic, evolving system, allowing scientists to predict interactions and mergers billions of years into the future. So why study the local group? Why do galaxies and other cosmic formations so far away actually matter? The local group serves as a natural laboratory for studying galaxies. Because it is relatively close, astronomers can observe individual stars, gas clouds, and galaxy interactions in far greater detail than in distant systems. By tracking how galaxies orbit, collide, and merge, scientists can study the processes that shape galaxy formation and evolution. The motions of stars and dwarf galaxies also reveal the presence and distribution of dark matter, the invisible substance that dominates the universe's mass. In this way, the local group offers a hands-on opportunity to investigate fundamental cosmic forces and test models of how galaxies grow and interact. The local group also plays a key role in measuring distances across the universe. By observing Cepheid variable stars, supernovae, and other standard candles within nearby galaxies, astronomers can refine the cosmic distance ladder. These measurements are essential for understanding the scale of the universe, the expansion rate, and the placement of galaxies far beyond our immediate neighborhood. Without the local group as a well-mapped reference, our knowledge of the broader cosmos would be far less precise. Studying the local group puts humanity in cosmic context. We live in one galaxy, orbiting an ordinary star. That galaxy is part of a family of galaxies, and that family is just one among billions in the universe. By exploring our small pond of the local group, astronomers gain insight into the vast cosmic ocean beyond, reminding us that even our familiar Milky Way is just one thread in a complex, interconnected tapestry of galaxies. This perspective helps us grasp the enormity of the universe while appreciating the unique vantage point we occupy within it. To recap, the local group is our cosmic neighborhood, a gravitationally bound collection of galaxies spanning roughly 10 million light-years. At its heart are the three largest spirals: the Milky Way, our home; Andromeda, slightly larger and slowly approaching us; and Triangulum, smaller and orbiting near Andromeda. Surrounding these giants are dozens of dwarf galaxies, small and faint, yet crucial for understanding galaxy formation, dark matter, and the evolution of the group as a whole. Together, these galaxies form a dynamic, interconnected system, a local laboratory where we can study the processes that shape galaxies across the universe. But this is just the beginning. In Episode 2, we'll zoom in on our own galaxy, the Milky Way, exploring its spiral arms, its central supermassive black hole, and the hundreds of billions of stars that make it our home. You'll see the structure and activity of the galaxy up close and understand how it fits into the larger story of the local group and the universe beyond. As we reflect on the local group, it's humbling to realize our place in the cosmos. We live on a tiny planet orbiting an ordinary star, which itself is part of a massive spiral galaxy. One galaxy among dozens in a single neighborhood, and that neighborhood is just a tiny piece of the vast expanding universe. Studying the local group reminds us that even in a universe so immense, careful observation and curiosity can illuminate our home and our cosmic family. As always, thank you for watching. If you enjoyed this video, please consider leaving a like and subscribing for more content like this. Also, feel free to leave in the comments ideas for what you would want to hear about next and your favorite fact from the video. Take care and never stop exploring.